Present. Hi, welcome to a new podcast episode. In this episode, we being Alan and Thor, we're going to walk through the undetectable inflation bug and try and explain what went wrong and why it went wrong and how to avoid similar situations in the future. So with that said, let me share my screen and then I can show you where things are at. Screen sharing is on. Very good. Let's go to the documentation. In the transaction, there are 4 fields that you need to be aware of. First of all, there's the inputs and the outputs. These are lists of not of UTXOs, but of cryptographic commitments to UTXOs. The addition record is just a hash, and the removal record is something more complicated that enables detection of double spend attempts, but for all intents and purposes, you can think of it as a hash as well. The point is that when the addition record and the removal record refer to the same UTXO, those two records, those two records are unlinkable. Other fields in the transaction that you should be aware of are the fee, which is the difference in amounts between the inputs and the outputs, and it is an incentive for the miner to include your transaction in their block. And lastly, there's the Coinbase, which is it contains the block subsidy, and so the miner is allowed to set the Coinbase in the transaction that ends up being the single transaction in that block. And he's only allowed to set the Coinbase to the allowed block subsidy. In regular transactions that non-miners initiate, the Coinbase is not allowed to be set.
Fee and Coinbase are amounts that are publicly visible, but the amounts in inputs and outputs are concealed behind multiple layers of hashes and whatnot.
Correct. And so we have a zero knowledge proof that establishes balanced transactions, in addition to other things. Getting to that, how is validity defined for a transaction? Well, for starters, we want to have a single valid proof, which it needs to establish balancedness, needs to establish that the owners assent to the funds that are being expended, and so on. And we can and do have a single proof to that effect, but it is unfortunately rather expensive to produce. You need a beefy computer to do it if you want to do it in a short amount of time. And in order to get around that limitation, we have an alternative, which is the proof collection, where you split that one giant program that verifies everything up into sub-programs that can be proven individually, and therefore you have a smaller task. And the big task is when you combine all those proofs. I guess the documentation is a little outdated because we don't mention proof collection here, but that is the right rule. So if you want to know what a proof collection looks like, you need to look at the diagram down here, and the programs that are being proved are the bold text here. So in the removal records integrity program, we look at the transaction kernel and produce a hash of the list of input UTXOs that corresponds to the removal records that are the inputs field, right? So remember that a removal record is a cryptographic commitment to a UTXO, so we're interested in the list of pre-images under that mapping. Collect lock scripts iterates over all the UTXOs on the input side and not on the output side, only on the input side, produces a list of lock script hashes, and then you still need to produce a proof for every lock script hash in order to establish ownership.
Absolutely, yeah, and this lock script proof functions like the signature does in Bitcoin. It is the owner's assent agreement to not just the funds being spent, but to this specific transaction.
Right, correct. And then kernel to outputs, just as removal records integrity computes hash of all input UTXOs, so does kernel to outputs compute a hash of all output UTXOs. And so with the inputs and output UTXO lists, we can collect all the TypeScripts. So basically in this program, we iterate over all the UTXOs and collect all the TypeScripts that we see there. And
hold on, yes, what is a TypeScript?
So a lock script determines who can spend the UTXO. A TypeScript determines how the state is allowed to evolve. And so for native currency or even any currency, what a TypeScript would enforce is that there is no inflation taking place. But you can imagine for a user-defined token, there has to be a mint, and the mint needs to keep track of the total amount of tokens in existence. All that state information, it would live on the UTXO, but it's the TypeScript that enforces that that state evolves correctly. So right now we only have two TypeScripts: the native currency TypeScript, which deals in amounts, and the time lock TypeScript, which prevents you from spending UTXOs before the time lock has expired. But in principle, you can write your own TypeScript, and the network won't notice that you have your own TypeScript, because all of this is in the end hidden behind a single proof. Yeah, so collect TypeScript assembles the TypeScripts of all the UTXOs in the transaction, and then you prove the correct execution, or you prove that you know the TypeScript corresponding to that hash, and you know a way to make that program halt gracefully. For every TypeScript not in that list, because you don't do it twice for duplicates, but in the set of TypeScripts, you do produce a TypeScript proof.
So this, what we're talking about here, is an inflation bug, and it's the native currency TypeScript that enforces the no inflation rule. So maybe it has something to do. The bug has something to do with the native currency.
Yeah,
TypeScript.
Yeah. This picture looks correct, right? But it's actually missing something, because in this guy, collect TypeScripts, we're only collecting the TypeScript corresponding to the native currency if there is a UTXO in the inputs or in the outputs that deals in native currency. At first thought, that seems natural, right? You don't care about TypeScripts that you're not dealing with. Except in our particular case, and right now we need to go back to the transaction data structure, we're always dealing with native currency because there's a fee and there is a Coinbase. And so in particular, if you produce a transaction that has no inputs and no outputs, then the native currency TypeScript is not being enforced. And so your fee can be anything. And so that's how you would exploit this bug to inflate the currency.
So that means in the naive way of exploiting this bug, you would set a very, very high fee, and a miner would then no.
Mine a lot. Yeah.
A miner would, yeah, a miner could make a transaction with a very high fee and could then reward themselves a very big block reward.
Yes.
So that would be publicly visible.
Yes.
Because the fee field is publicly visible.
Indeed. But we also have such a thing as merging transactions. So if we go back to the rules that make transactions valid, another rule is a transaction is valid if it results from merging two valid transactions. And so you could make that high fee transaction in combination, high fee zero input, zero output transaction in combination with another transaction that looks totally legit, and then merge them, and now you just have a legit looking transaction that happens to have a high fee. Good luck determining that that was malicious. And it's actually a step worse than that, because you are even allowed to produce transactions with negative fees and merge those into other transactions, and now you can gobble up your fee. This is what a proof upgrader is doing when they upgrade your proof collection transaction to a single proof transaction. They want to collect a fee for that work, and in order to do that, they merge your transaction with a transaction that has a negative fee and UTXOs on the output side that they control, which we call a fee gobbler. And this is where things start getting very dangerous, because if you put all those pieces together, you produce a transaction with no inputs, no outputs, and a very high fee. And then you merge that transaction with the fee gobbler. Now you have a transaction that still has no inputs, has positive outputs, and has zero fee. That's an inflation bug. And if you merge that transaction with something that actually has inputs, then it's completely undetectable. So it's not the bug that's undetectable, it's the resulting inflation if it is exploited, in case there was any doubt about that. All right, that's the high-level perspective from the documentation. Let's have a look at the code.
Absolutely. Let's have a look at the code. Maybe I could just draw an allegory to Bitcoin first. It is as if we were doing the no inflation check on all transactions, except when the transaction had no inputs, no outputs, but a positive fee. In that case, we said, we don't need to do inflation check here, but we still do. We still need to do, and that's what the fix is about. Right? Always doing the inflation check.
Indeed. All right. So looking at the code, I just verified that we are on branch master. So this is the code that was live up until not last Friday, but the Friday before.
2 weeks ago. Yeah.
And we're looking in directory transaction validity collect typescripts. This file is responsible for the collect typescripts program, which collects all the typescripts from all UTXOs on the input and on the output side of the transaction. And so we have an implementation of this program in Triton assembler, which we call TASM, and we have an implementation in Rust. Now, the Triton assembler implementation is the one that runs on the prover. So if there is an inconsistency between these two programs, then it's the TASM code that defines what the blockchain approves. But it's rather difficult to read the TASM code. Here you see it. And we try to keep these programs lockstep in sync. And so the reason why we're not using Rust idiomatic expressions is because we still need to translate this to assembler code. And so it's easier to make that translation if it resembles C. Anyhow, the point is that we have a list of TypeScript hashes which we populate as we iterate over all the input UTXOs, and we push all observed TypeScript hashes after filtering out duplicates. And then we iterate over all the output UTXOs, and we push all observed TypeScript hashes after filtering out duplicates. And that's exactly the error, because if there are no UTXOs to iterate over, this list will have the value it had when it was initialized, which is the empty list. And so if we move to the reboot branch,
where we are fixing or have fixed this bug,
we will find a different story. We're still iterating over all the outputs, still iterating over all the inputs, but now we ensure that the list of TypeScript hashes is never empty. In particular, it always contains the native currency TypeScript hash. And that's the essence of the fix. What I find salient about this bug is that it's a very conceptual bug. You can describe what went wrong by pointing at pictures and data structures, and it's not related to the typical culprit of bugs like overflow errors or out of bounds errors, or using the wrong instruction in assembler. It's a very high level.
So the kind of bugs that you have been focusing on, or your approach to soundness of these programs have, to a large extent, been through cryptographic proofs or cryptographic properties, assurances, such that the hash of these outputs must match this other hash. That's your approach, and my approach has very much been, well, let's look at classical programming pitfalls like overflows and out of bounds accesses to lists and so on, and that has been my focus. Or invalid pointers, things like that has very much been my focus.
Yeah, and this one kind of fell in the middle.
Yes,
because it's not a cryptographic vulnerability, and it's not a memory hidden state vulnerability either.
Yeah.
So what can we do to catch this sort of bug in the future?
Yeah, well, the way we discovered the bug was I was working on validity checks of primitive witnesses, and you were showing this list of how a transaction can be valid. That was step A up there. The first thing you do in order to prove that a transaction is valid is that you assemble something we call the primitive witness, and it contains your secret keys that you should not share, obviously. So you need to do the transformation from the primitive witness to the proof collection locally on your own machine before you can share it with the world. And we have test case generators for these primitive witnesses, and we have validity checkers of these primitive witnesses. And I was working specifically with the validity checker, validity checker of primitive witness, and I said to you, hey, we need to ensure that the native currency witness and native currency TypeScript are always present because of the existence of the fees in this particular primitive witness validity check. And then you were able to generalize that insight to an insight of the transaction proofs, the things that you can share with the rest of the world. That guarantee was also not present there.
Yeah. And so how likely is it that there are other similar vulnerabilities waiting to be discovered? And how can we catch them?
We catch them by staring at the code long enough. We catch them by
reading and writing documentation.
And reading and writing. In this case, it was tests. those
Yes.
tests that caught it. We were building big, complicated tests, and
I remember we were chasing an off by one error, or what is it, a missing element in a list, single missing element in a list error, and we were confused. Why isn't the list of TypeScript hashes populated in the way we expect it to be?
yeah, we have good test case generators, but those test case generators have not always been checked as thoroughly as they should. I think we are a lot better there than we were previously. How do you guarantee that there are no further bugs, right? Well, you try to keep your checks, your state, the things that you need to guarantee. You try to keep your checks as simple as possible. That means that there are fewer pitfalls. But can you ever provide 100% guarantee that there are no oversights? I don't think so. Like, you can do some kind of proofs of the integrity, I guess, but with proof systems and whatnot, you can certainly do something there. But a final guarantee, I'm not even sure Bitcoin can boast of such a thing.
No, I was thinking about formal verification. In theory, you could formally verify every character in the entire code base and prove statements about inflation being impossible, except through mining. But even Bitcoin doesn't have that, right? Bitcoin has the largest bounty on it for finding an exploit, and one way to find exploits is to start writing a formally verified version of the source code and seeing where things break down. And I'm sure tons of people have tried doing that, but it's just such an infeasibly complex task that they haven't gotten very far, which is why we still don't have a formally verified implementation of Bitcoin. But that's at least a very distant goal to live up towards down the line, very far down the line. Yes, we would like to have a formally verified guarantee that inflation is impossible. Until then,
we have to rely on test case generators to spot discrepancies between our various validity checks. We have validity checks on various of the proof system, so we can check is the primitive witness validity, does that always correspond to a proof collection validity? Does that always correspond to a single proof validity? And then we have dual implementations of all our consensus programs. We have an implementation in Rust, we have an implementation in TASM, and we can check that they manipulate the VM state in the same way, and we can check that they
which is a stronger thing than just their input-output behavior being identical, right? Because
yes,
we also check that the state of the VM after execution is identical, which is not considered part of the output.
and we check other things when the consensus program has gracefully halted. We check that the inputs, various kind of inputs to the VM are empty, that the stack ends up empty. Yeah, so I think we have a lot of tests and test case generators, dual implementations of the consensus programs, cryptographic assurances, also bounce checks on our lists and arrays and size indicators. A check that a U32, if a word is supposed to represent a U32, that it is actually a U32 and not something bigger than that. We have lots of these checks. I'm pretty happy with the state of our code base, and it wasn't a classical software engineering oversight. That was the problem here. It wasn't an overflow. some addition. It was yeah, something more removed from these classical checks that you would do as a software engineer.
All right, I guess that's it. Take care. Stop recording.